All right, as I was trying to say, if you folks want to catch up on this slide deck later, you can see the individual slides or download the whole presentation at openoid.net/presentations. You can actually get the decks for any of my presentations there. I keep them all. All right, so what we're going to be talking about today is routing with Linux. This is it's really kind of basic stuff. We're not talking about anything that I wrote any code for or did anything all that magical. I basically just put together a simple IP tables rule set to do the things that we would expect a normal Soho router to do, and talk a little bit about what I found out doing it. Probably not a real problem in the lug, but I like to put this slide in here for the big shows, because you get some folks that come in and they're not quite sure what they're getting into, and this is going to be an extremely technical presentation, because what we're going to do is after we talk a little bit about what we're doing, we're going to walk all the way through the config files, including IP tables, DHCP daemon, and bind for getting everything set up to build your own router. All right, so the first question seems kind of stupid, but what actually do we consider a router? And the answer is not just routing. We expect a router to provide DHCP service. We expect it to resolve domain names for us. We expect it to actually route packets. We also expect it to be a firewall and accept some packets and deny others. And we want network address translation. This is an image that I took for the Ars Technica article that I wrote about this stuff. And we look at a few fairly common commercial Soho routers. And over on the left, that little silver critter with the disco lights in it is a generic Linux PC that I did what we're going to be talking about today on. I tested all those routers together, and when I first started writing the article for Ars Technica, I thought that article was going to be what we're talking about today, which is basically just going through the configs and how to do this. But I wanted to do some testing and be able to demonstrate that it was a high-performance solution before I actually wrote the article. And what I discovered really quickly was that, somewhat to my surprise, the performance really was the big story. So that Ars Technica article actually ended up being more about the performance of things. So given that the performance was a little bit of a surprise to me, why would we do the Linux router? Why would we start with a bare copy of the Ubuntu server rather than a purpose-built router distribution like DDWRT or OpenWRT or pfSense or SmoothWall or IPFire, blah, 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 blah. The list goes on. So why would we do this all over again from scratch? And, so performance is good, but I honestly didn't expect the performance to be any better given the hardware doing this from scratch, versus using something like pfSense or IPFire. I got surprised, but that really wasn't the important thing. The big thing that I wanted was reliability of knowing I got to pick the components on my hardware and they're good server-grade stuff. I wanted the flexibility. Flexibility in this case, I use OpenVPN really heavily in my day-to-day work, and I'm very accustomed to using it the way that you're supposed to from the command line without a GUI helping. And so the help, I find, often gets in my way pretty badly. This was really nice because I could just do exactly what I always want to do. Security was the biggest key for me. I have to be really paranoid these days. I had a very unfortunate incident with a young gentleman from Romania back in 2011 that taught me to care a whole lot more about information security than I used to. And it frankly makes me nervous with traditional commercial router offerings. You get a firmware on the router that comes out of the box. That firmware is likely to be 3 years old. You can update it with something that comes from the vendor, but it's all proprietary. You're lucky if it gets updated once or twice a year, and when it does, it's usually to add shiny new features more than it is to fix bugs. So all that is a little scary these days to me. And finally, master. If there's anything that you don't already know about setting up Linux networking, you're liable to learn it by going through this project. Oh, that is some loud people. All right, so with that said, which Linux distribution are we going to use? I used Ubuntu, and just like it says on the screen here, if you don't like it, you can write your own how to build a Linux router presentation. I'm a big Ubuntu fan, and again, I initially.
Oh, it's still showing slide one.
I don't know what to tell you. Still showing. Can anybody bring it up on a machine here and see what they're seeing?
Yeah.
I wonder if the full
If
screen's
I do
not
it,
doing
I'm
that.
gonna hijack your session. So, I'm gonna do it.
Ask if their screen just updated.
Yes, it did.
Okay.
So where you did.
All right. I guess we can't be in presentation mode then. Yay!
Did-
Google Hangouts.
Yeah. Yes. Yeah.
Okay. Yeah. The screen share must just not like full screen mode.
Yeah. That's it.
All right.
So
So for those of you who couldn't see this in full screen, the only slide that you missed that really matters a little bit was this one. Just looking for pictures of the routers. And this big Batman-looking thing in the back is a Netgear Nighthawk X6. That was about a $285 router when I bought it. Those things are amazing, you know, considering it's something that you can buy at Best Buy or Staples. They've got a smartphone grade ARM 1.2 gigahertz dual-core CPU in there, and they do a really, really good job. This little critter right here is a Buffalo that I literally just had moldering in a desk drawer. It's a 100 megabit router. It doesn't even have gigabit interfaces on it. And I brought it out just for something on the extreme low end. And then this little critter right here is a Linksys, and my criteria for purchase on that thing is it was the cheapest thing at Staples that claimed to be a gigabit router. I'd love to tell you it was worth every penny, but really it's not. All right, so back to where we were. I used Ubuntu Linux. Why? I really, really like Ubuntu Server. That's the distribution that I work with professionally as much as possible. It's very, very stripped down. The base install is an extremely clean command line interface. People have the concept of Ubuntu as this big, heavy, you know, do everything for you, everything's already installed desktop operating system. If you start out with Server, it's actually leaner than Debian on a bare install. You get apt package management, which is a huge plus for me. It's definitely my preferred package manager. And one of the biggest things is you get predictable long-term support. Nobody else, in my opinion, has long-term support figured out quite as well as Canonical does. If you install an LTS release of Ubuntu, you have 5 years of support before you have to upgrade. That's already pretty nice, given that Debian's support cycle is until we don't, and so is BSD's and most of the other distributions. And some of them will offer a very long support cycle, Debian and BSD being good examples of that. But again, it's until we don't, and you can get surprised at really inconvenient times by that. I got surprised a few really inconvenient times, and I don't like that anymore. The last piece of the package is not only do you get 5 years, but you can't ever forget when your 5 years runs out on Ubuntu. Because like on this laptop right here, we're running Ubuntu Trusty, which is a long-term support release. Trusty's version number is 1404. That means April of 2014 is when it was released, 4/14. So in April of 2019, it's going to leave support. Between now and then, because they release a new LTS every 2 years, you have 2 opportunities to upgrade. In 2016, which of course is already here, you can make your decision whether you want to upgrade to Xenia or not. You can either do that or you can pass. That 1804 will come out and you'll have a year to get onto it before your support expires for Trusty. That's pretty sweet. I can't really get that out of anybody. Even with Microsoft products, you have a very long support cycle, and it is planned out ahead of time. But you have to, go find a web page and look up the thing. I still can't remember off the top of my head exactly when support ends for 7. All right, so this slide originally said I like a GUI, so then try an x86 build of DDWRT. Since I gave this presentation the first time, I learned a little bit more about DDWRT, and I really, really don't recommend you do that. There has not been a stable release of DDWRT in over 8 years now. When I first started looking for DDWRT, an x86 build of it to install on this hardware, I went to the project website and looked in stable releases, and the last thing I saw was from 2008, and I thought, well, clearly I'm just, I'm not looking right. No. I was looking in the right place. They haven't had a stable release in 8 years. They do a new beta release every few weeks to every month or so. But unlike some open source projects where they just keep calling it beta forever, but it's really quite reliable, now they mean it with DDWRT. All kinds of things are broken in those point releases. If you are running a raw DDWRT project beta release, you will not have to look hard to find bugs. They will be glaring and obvious and world-breaking. So the question is then, all right, well, if I'm telling you DDWRT sucks so badly, then how come so many of you have good experiences with it running, replacing the original proprietary firmware on commercial routers, little NIP stuff? And the answer to that is some semi-anonymous person with a colorful name like, Skull Candy or, Brain something or another or Kong has gone and basically hunted through these point releases and found all the bits and pieces that weren't broken at any given point in time and reassembled into a functioning, working whole. So, and they, like Kong, for example, builds some pretty solid releases of the DDWRT firmware for Netgear R7000 routers and a few other models. And they do work, in my experience, well and reliably, but still, you put yourself on the end of the supply chain that includes some dude named Skull Candy or Kong who's looking for little bits and pieces of something insanely broken to glue it together until it works, and then supporting it as long as he supports it until he doesn't support it. That's just not good enough for me. So the better option, if you like a GUI, if you want to be able to run on x86 hardware, but you're just not feeling up to this whole command line only thing, try an x86 build of pfSense. pfSense is very solid. It's got really good feature set. And it'll show you a pretty fair number of pretty graphs. You can do QoS, you can do VLAN tagging. You can actually do a hell of a lot more with pfSense than you can do, at least with how much we're going to talk about today of the bare Linux build, because we're not really going to get much any further than just routing, firewalling, NAT, DNS, and DHCP. We're not going to get into VLAN tagging or QoS, prioritization, none of that stuff. I can tell you pfSense, it performs pretty well. It does not perform as well as what we're going to look at tonight. Also, if it matters to you, pfSense is BSD-based, not Linux-based. So I keep talking about performance. This was the headline graph out of that Ars Technica article, and it kind of blew me away. The blue bars on the back are an initial test, running my test suite over localhost on a single server to make sure that Nginx, which was the workhorse that I was testing against, could actually handle well above and beyond anything I could throw at it over a network. And obviously that was perfect. I actually had to crop the scale on the graph because Nginx was actually delivering about 40 gigabit over the localhost interface. So that wasn't a problem. The next set of bars, the dark maroon in the back, that is just running direct across the interfaces from one server to another. Basically what we're doing is we're running Apache Bench against Nginx. And if you look at the labels down on the x-axis on the bottom, you'll see like 1024K-10, 1024K-100, and on down the line to 10K-10,000. And what that actually is the first number, the 1024K, that means 1 meg. That's a 1 meg file. And the -10 means we're downloading it with 10 client concurrency. So Apache Bench on the other end is trying to download that file as fast as it can with 10 clients running at once. If you look at 1024K-10,000, it's trying to download that 1 meg file with 10,000 sessions going all at once, and on down the line. And as you can see, even just across the network direct, you can see a definite impact on those maroon bars. There's no router at all in the way there. That's just running straight across a wire. And you'll see some pretty significant dips there. And what those are caused by is actually TCP window scaling. In particular, as you start hitting the 10,000 concurrent connections and the smaller file sizes, TCP has trouble figuring out how fast it can actually go. You might think intuitively that if I ask for 10,000 concurrent sessions, they'll each get 1/10,000th of my bandwidth. But it doesn't really work that way. They're all struggling, fighting like dogs trying to get their food dish. And one's going to get more and others are going to get less. And as the ones who got more finish, the ones who got less can start scaling up and getting more of the available bandwidth, but it takes them a while to do it, which is why you see that dip in the overall bandwidth available. is basically once you get towards the end of your run, all your runts that didn't get to the food dish, they're trying to finish up, and they don't really realize they've got the whole pipe available to them. So the cool thing is the next set of ours, the green one, that is the little Celeron router that I built using Linux, and it doesn't look any different than the maroon one. There's one spot where you can see it being a little bit lower, but basically this thing is just like a network condom. Whatever bandwidth you've got, it's going to give you exactly that. Whatever you throw at it, you are not going to phase it, which is pretty awesome. Now, I really wasn't sure ahead of time. I didn't even know if I could perform as well as that Nighthawk X6. I was a little scared of it. Like I said, I mean, it's got an ARM A9, 1.2 gigahertz dual core, and I had a little bit of the fear that, hey, this thing is purpose built to do what it does. Maybe it's going to kick my ass. As you can see, it emphatically did not. If you're running gigabit, if you're lucky enough to have Google Fiber or some other way to get gigabit internet access, you will see a huge difference between something like that X6 and one of these little custom routers. Even if you're only running, the best we can get in Columbia here is Time Warner 50x5. And if you push it far enough, you can find some places down there towards the end when we're looking at, running a lot of sessions of downloading those little 10K files over and over again. That Nighthawk gets its ass kicked to the point where you'll see it even over an internet connection down here in Columbia, South Carolina. Thought that was pretty cool. Then your next set, of course, is that Linksys. Like I said, my only criteria there was cheapest thing at Staples that said gigabit. And it did an excellent job of demonstrating that, yes, your router really does matter. Pretty much across the board, that thing is delivering less performance, even on like Time Warner internet scale, than the Nighthawk or my router. So that's worth noting, especially if you're doing something challenging, like any kind of peer-to-peer file sharing. You will see a huge difference going from a crappy little Linksys router to something that is fairly serious. And then finally, I thought this was pretty interesting. That little Buffalo that I dug out of a shelf, it actually beat the Linksys in some of the tests, despite only having a 100 megabit interface and being about 7 or 8 years old and having just languished in a drawer. All right, so now that we have some idea of what we're doing and why, let's look at the actual nitty-gritty. What's our plan here? We're going to need to, of course, first we install Ubuntu server, and I'm just going to take it for granted you guys can make your way through an install. But once we're done with that, we're looking at command line. We need to configure the network. We need to enable IP forwarding in syscontrol.conf. We need to set up DHCP using IC DHCP server, DNS with bind9. We're going to set up network address translation. That's going to be part of our IP tables rule set. And then we set up our firewall rules, also with IP tables. Step, configuring the interfaces. This is done in a plain text file located at etc. network interfaces, Ubuntu. And your loopback interface should already be set up. Then you've got your WAN interface and your LAN. Now, you're going to need to identify physically which interface you want to use for which thing if you're using generic hardware like I was, because it's not just going to conveniently already say WAN and LAN on it. The other thing is, once you pick that interface and once you figure out what's P4, P1, or what's P1, P1, and which you want to use for which, label it, both in the comments in your interfaces file and physically on the router. It will be a giant pain in your butt later on in life if you haven't actually cleanly marked this everywhere. So for the WAN interface, it's very easy. We just say inet DHCP, and that's it. On the LAN, we're going to say we're going to need a static interface. In this case, I decided that I wanted to use the subnet 192.168.99. The router is going to live on .1, and our net mask 2525250 says that we're going to use the whole class C at 192.168.99. After you've done that, the cleanest way to get all that loaded is just to go ahead and reboot the machine. You used to be able to just do etc the networking restart, but for whatever reason, Canonical nerfed that a few years ago. So you pretty much have to reboot the box if you don't want to get into some serious wizardry to reload the network stack. Once you've done that, you need to enable IPv4 forwarding. That's going to be done in etc. syscontrol.conf. The line is already there and commented out. All you have to do is uncomment it. So without the pound in front, just net IPv4 IP forward equals 1 to turn that on. And once you save the file, you can do a syscontrol-P to load that. It automatically every time you reboot the box. Now, at this point, once you've uncommented that, your box will cheerfully forward traffic from one interface to the next, no matter what. It won't do any network address translation yet, but if it hears traffic that it thinks should go on the WAN interface and the LAN interface, or vice versa, it will chuck it on where it needs to go. All right, DHCP and DNS is actually pretty simple. Go ahead and do a quick app update, and then install ISC DHCP server and bind 9. The configuration for ISC DHCP server is pretty easy. In dhcpd.conf, you just do a quick block like the one you look at there. Define your subnet, which will be the same one that you used in interfaces. Your net mask, again, the same. The range is going to be, of course, the range of addresses that you're automatically handing out. The box's own address should be the router. It should also be the domain name server, and you'll want to define the broadcast address at the end of the subnet. Once you save that, you can just restart ISC DHCP server, and presto, you're handing out IPs. Bind 9 will not need any configuration whatsoever unless you want to define some forwarders in it. It's actually already resolving DNS for you right out of the box. All right, so now what we're going to do here is this is the part where all this stuff is simple. Now we're going to get the part that's a little more complicated, the actual IP tables rule set. And we're going to do this in little bite-sized pieces so we can talk about each of them. Because you're not really going to be able to see the whole thing on the screen at once. Starting out, we want to create the script. There's a directory on Ubuntu or Debian called etc network if-preup.d. I really love the networking setup that Debian and its derivatives use. Any script that's in if-preup.d and is executable will get executed before the interface is brought online. So this is the perfect place to substantiate your IP tables rule set. Just before the network interface is brought online, it will make sure that your firewall works so that you never have a race condition where your network interface is up, but your firewall hasn't necessarily applied quite yet. And the barest bones of that script is going to look just like what you see in the bottom. We're going to do a shebang to bin sh, and the barest part is we're going to do sbin IP table restore, angle bracket, EOF. And then we have an EOF at the end of the file, and we stick rules in between. Now, the reason that we're doing that is because IP tables and IP tables save and IP tables restore, they do not accept variable declarations, which is a real pain in the butt. So you end up having to remember, okay, my WAN is P4, P1, and my LAN is P1, P1, and you will forget, and it will suck. So if you do it this way, what we can do is we can declare variables before that IP tables restore line, and then we can use the variables in the rule set that we have in between the IP table restore and EOF, which makes life much more convenient. All right, when you look at how IP tables work, you have several tables. Each table will have several chains. The table is going to begin with its own name, prefaced by an asterisk, and then default policies for its chains, which are prefaced by a colon. So on the NAT table, we've got chains for pre-routing, input, output, and post-routing. And we're going to have to do a default accept on all of those. Now the last thing is every table has to end with commit in all caps. If you forget that, or you get rid of one, you don't have a commit in between one table and the other, nothing is going to load and you're going to be confused and life is going to suck. This is one of the things that confused me a lot when I was getting started with IP tables. All right, looking at a skeleton rule set, we've got our NAT table. We're accepting everything and committing. We've got a filter table. We're accepting everything. Then we're actually going through and we're dropping input and forward. Now, we could have also done a default drop policy on input or forward. For whatever reason, my brain just likes it better to actually see the drop at the end of the rule set. I kind of like having it in my head that I want to be able to go all the way down to the commit and see a drop everything line to drop everything that hasn't been there before. A lot of people prefer to do it instead, have, in your policy declaration, say input drop, forward drop. I just like it that way, and you can do it either way. Looking at the NAT table itself, this is the line that really makes the magic happen. This was the bit that wasn't really familiar to me when I started this project. I'd been working with the filter table quite a lot in IP tables for years on servers to say, no, you're not allowed to talk to my MySQL service and things like that. But I hadn't really messed around with network address translation. A single line will pretty much do the trick. Oh man, I did not edit that slide. That should actually say, actually, well, I can edit that, can't I? I'll go ahead and do that live. So, well, no, we'll see it at the end. We would have declared our, WAN equals P4, P1, so we could see, we could say A post routing, O WAN, J masquerade. But basically, that's it. You want to say that for your post routing chain, anything that's going out the WAN interface should be masqueraded. And that's really all there is to that. All right, getting to the filter table, that gets a little more interesting. So we're still accepting everything by default on input, forward, and output. And there are a few things that we want to do a global accept on. We don't even want to think about it. ICMP, there are some people who like to drop or deny ICMP packets. I do not like doing that. It can have some really unintended consequences. And frankly, I'm not that worried about somebody being able to ping my box. If they think it's there, they're going to find it one way or the other. So I really don't mind them being able to get a ping return. So I'm going to go ahead and accept anything ICMP. Anything on the loopback interface, if you aren't accepting anything on loopback, you are again going to cause yourself some really interesting problems down the line when things don't work in ways you didn't expect to have problems. We're also going to accept anything that's established. We're doing connection tracking here. And so that final line in that first set of three where it says input M state, state established, J accept, that basically just means if I've already processed a TCP connection for anything here, if I've already accepted that connection, I'm just going to continue to accept it. I don't need to like pass all the way through the rule set to figure it out for every single packet that comes down the pipe. All right. Now the traceroute part, that was kind of cool. It's surprisingly hard to figure out how to make traceroutes still work when you've got IP tables running. There's a lot of stuff on the internet that's talking about, ICMP, accepting ICMP traceroute protocol. And the thing is, that won't do you any good for almost anything. There are actually two different types of traceroute commands, and one uses ICMP, and I've never actually seen a client use it. When I looked it up, I saw something obscure that actually used ICMP traceroute, but that's not what anything in the world you're used to using does. Whether you're talking about a Linux client or a Windows client, their traceroute commands both. What they actually do is kind of stupid. They send a UDP port, a UDP packet to a random port between 33.434 and 33.523, and they expect it to be rejected. And if it's not rejected and bounced back, then the traceroute doesn't work. So when you do your standard IP tables rule set and you're just dropping anything that you don't know about, including that traffic right there, that's why your traceroute don't work, why they stop there. And hilariously, the couple of pages that I found that did actually talk about this were recommending that you accept that traffic so that your machine could then bounce it because it didn't have a service running. Of course, that's stupid because that means if an attacker then sets up a service running on UDP in that port range, they'll then be able to talk to it through that gaping hole you left in the firewall. So what we want to do here is we just want to make sure that we reject those packets rather than dropping them, and all of a sudden, presto chango, your trace routes work. All right. Now from the LAN, we want to accept we want to accept DNS, SSH, and DHCP client requests. To do that, we need to accept port 53, either TCP or UDP. A lot of people make the mistake of only allowing UDP 53 for DNS. It turns out that you can get surprised at when it decides to use TCP rather than UDP. There's not a whole lot of control you have over that. And if you're blocking TCP, then you'll intermittently have issues with DNS and not be real sure why you are. So make sure to open both of those up. I notice also we're doing the -IP1P1 here. That's our LAN interface. We're not accepting this stuff from the WAN side. We are only accepting that from the LAN interface. We're also accepting SSH, TCP22, the UDP 67 and 68. That's what you need in order to accept DHCP client requests. And finally, we're dropping everything. A input, J drop. We haven't already accepted it. We ain't gonna. All right, forwarding. Anything that's established, we're going to forward it. Anything going from the LAN to the WAN, we're going to forward it. Anything else, get out of here. Not going to happen. So any traffic that's coming from your WAN. One thing that a lot of people don't realize is that a sufficiently clever attacker on the WAN side of a router If they can manage to get a packet to your router that has a destination to your non-routable LAN address, if you don't have a rule that's dropping forwarded traffic, it will cheerfully go right the heck on through. Now that's pretty difficult to accomplish from arbitrary locations on the internet. You usually would need to have control over an IP in the gateway subnet directly on the other side of your router to make that work, but you don't want to take chances with that. So just go ahead and make sure that you drop it. Don't rely on network address translation itself being your protection. You need to actually be dropping traffic from the WAN that's going into the LAN, unless it's related to an already established session. Now, all right. This part used to just confuse the living hell out of me. This took a little bit of research to get it working when I set this thing up. Port forwarding. We're doing a very simple port forward here. We're just allowing traffic for HTTP port 80 from the WAN side to the LAN side. We're running a web server on the inside of the LAN. We want to forward that through. The thing that used to confuse me is I didn't really realize you have to have matching rules in 2 separate tables to make this work. You've got to open up a pinhole in the NAT table on the pre-routing chain first. So for TCP on the WAN interface that's going to port 80, we want to do DNAT to the LAN address of our web server, which in this case we said was 99.100. Now you need a matching forward rule in the filter table. And we want to say forward any TCP traffic that's destined for that machine, accept it to go to that machine, because otherwise that's going to be getting dropped to that default drop, non-related traffic rule that we had before. If both of those rules aren't in place, your pinhole will not function. All right, so at this point, we actually have, if you applied all these changes in order and bounced the box, you would have a fully functioning router. It would be handing out DNS, it would be handing out DHCP, it would be letting the stuff out the WAN it's supposed to, blocking the stuff coming back from the WAN it shouldn't, and doing all the things that you would expect it to. This slide right here, of course you can't see right now, but the goal is not really for you to read that slide where it is. The goal is that if you go back to our first slide and you look at where you can download the deck from, wow, that's not what I'm going to do. So if you look at the deck at openoid.net/presentations, you can download this whole presentation and you can copy and paste that entire rule set directly out of that slide and into a text file to work with it directly, which makes life a little easier than trying to go through and do all the little bits and pieces in order that we talked about one at a time. And that is pretty much that. We just set up a router. If anybody wants to see the hardware that I use for this, let's see if we can get getting out the back of the camera. Oh, there we go. Stop sharing. There we go. So, okay, yay. For anybody who's not here, this is the critter that I use normally. You can see we've got 4 interfaces on it, and they're marked LAN 1 through LAN 4 on this device. So again, get your handy dandy label maker out, figure out which one you're using for the WAN, and put the sticker on there that says WAN. Otherwise, you will have a bad time. But this is just a generic little, it's a Bay Trail Celeron J1900 generic small form factor PC. You can see we've got an actual VGA out, so you just plug a monitor, keyboard, mouse into this thing, and it's just a normal computer that happens to have 4 Intel gigabit NICs. This particular one has it's got a Kingston 120 gig solid state drive and 8 gigs RAM in it. And everything all put together ended up being about $240 I think. And it draws about, depending on what you're doing with it, once it's set up as a router, you'll draw between 9 and 12 watts as measured on my kilowatt. Anybody want to look at it? Local folks? You did.
So when you were going through building that, and actually I was going to ask, that device, so you've got multiple LAN interfaces there.
Yeah.
Is there any way that you can copy traffic from the inside to one of the others? Like say if you wanted to set up a snipper or a IDS?
Yeah, so basically the the way, when I the first device that I set up, it was Silver One that you saw on the slide, only had 2 interfaces.
Okay.
So I just had a LAN and a WAN. Actually, when I set those up, I set LAN 1 through LAN 3 up as a bridge, and then LAN 4 as the WAN. So at that point, it functions the way that you would expect, a standard commercial router to. You can plug cables into each of the 3 LAN ports and all go to LAN devices and do the thing. If you want to set them up differently, like if you wanted to set up like a monitoring port, I can't talk really intelligibly about the exact lines to do that, but yes, anything you can think of doing network-wise is not that hard to do. I'm not sure if you would want to I think you would just use a bridge port for that, honestly. Because if your device is in promiscuous mode, I believe it should see. I know it will. It'll see all the traffic on the bridge.
Okay.
So yeah, you won't capture. If you have anything on another switch further down in your network, you're not going to see that unless it comes from the switch to the router to head out. But like if you only had 3 devices, plus your WAN, then yeah, you could have one of those devices could be a monitor, and it would be seeing all the traffic that comes into the bridge, whether it was the 2 other computers talking to each other, or whether it was either of them talking out the internet. Wow, that's not so much a shill as a dick question, actually. It doesn't. It's not doing. We're not doing any internet scale routing. All we're really looking at is, I assume, RIP. We're not doing any BGP or anything like that. It doesn't know about anything further than the next interface. So, like, if you're trying to do exactly, no, we're not doing any of that crap. We're just doing RIP. It knows about its own interfaces, and it has a default gateway, so it'll fling anything it doesn't know about out of the WAN interface regardless, and hope the next box there knows what to do with it. But that's as far as that goes. We're not doing BGP or anything like that.
Ideal for putting this thing out there.
Yeah. At least so far. I mean, this is Linux. You can certainly set up BGP or any other routing protocol you want to. There's nothing limiting you. Any protocol you can think of exists already on Linux and BSD before it gets to the proprietary. It's just a matter of looking up man pages and implementing it. And I have certainly had no need to do that, so I haven't. Beyond that, I mean, you can of course set up static routes on it. But I've never personally needed to implement something like BGP, so I don't know anything about it. I know one thing about it. I know that one of the packages, at least back in the day, that you would use for that was something called Zebra. There's my knowledge of it. Anybody else got anything? Deal.
Does anybody from the internet have any questions for Jim?
On the internet.
Yeah. Okay.
Well, I think that's it, folks.
All right. Well, thank you all for attending, and we'll this presentation will be available on YouTube, and we will chop out the crappy setup parts that I was fumbling with. We tried to test it as much as possible, but we haven't hit a home run yet, so we'll try for next one. See y'all later. Thank you.